Okay, great. All right, guys. Please welcome to the stage. We've got Luis Miras here doing his talk on reverse engineering. So please give him a big round of applause and welcome him to the stage.
So good morning. Hope everyone's doing all right after last night. And this talk's on C++ reversing, how it's different from C reversing, how we can use disassemblers and debuggers together. It's a little bit of a continuation from my talk at DEF CON. So I'm going to review some of the stuff I covered there just as an overview, and then I'm going to go into what's specific to this is my blog. I haven't posted in a while, but all this, the code that's on here, the slides from DEF CON and from here will be posted there pretty soon. And if you want to email me for whatever reason, there's my email. So this is a little bit about what I'm going to cover. I'm going to cover what I call the different phases and what needs to happen to bring reverse engineering to the next level. Right now, there's a lot of holes and things that are missing to make it a complete process, and a lot of things that could be done better. Then I'm going to cover some review on C++ and the specific problems that, as a reverse engineer, we face that makes things a lot more difficult. Then I'll cover various solutions, some discovered by me, some discovered concurrently by me and someone else, and other solutions that other people have worked on and discovered themselves. Then I'm going to talk about the future roadmap, where this should be going, and part of that is phase 3, which is what I refer to as a software JTAG, and go into that. So a little bit of an introduction. C++, I don't know how many of you guys have started reversing C++, but there's lots of differences. The first thing is that you have objects, you have vtables, you don't have direct calls. A lot of things are called through registers, so all your cross-references are messed up. Let's say you're reversing something, you find a vulnerable function, and the one path that you know about through the runtime analysis, you can't overflow. But you want to know what other paths, what other code paths can you get to that vulnerable function. It's really hard without having some type of cross-references and really examining the vtable to see how you can get there. So this is a lot of what the talk's going to cover by using the static analysis provided by IDA, some analysis scripts, and also using runtime disassembly together to create a loop. So you use IDA, then you use your debugger, and you start feeding information back and forth so that you get information back from runtime, feed it back to disassembly, reanalyze, and you keep on going until you get a good hold of all the software you're trying to reverse engineer. So this combination is it yields a lot more results. What I'm really trying to do here is, reverse engineering is really slow. You know, it takes forever. And if there's stuff that we can do that optimizes it, we run through, let's say, some test code, and it starts feeding and filling out disassembly commenting code for us, then that saves a lot of time. It'll make finding vulnerabilities faster and more efficient. So these are the phases I think that need to happen to be able to make reverse engineering faster and more successful. The first thing is symbolic information being passed from disassembly into the debugger. Right now, what's available into, let's say, Ollie debug or WinDebug, soft ice is end of life, so I'm not really worrying about that. But right now, the only type of symbolic information we have are map files. Map files just tell you where a function is, what the name is. That kind of helps out, but it's not enough. So to work on this, I started working on a couple different IDA plugins. The first one is going to generate custom PDB files. So you take your disassembly from IDA, and all the functions that you've named, all the structures, all that stuff is put into a PDB, and the PDB can be loaded into the debugger. So now you're not looking at like 04x317 or whatever. You're looking at main. You're looking at read stream. You have a name, and you can correlate directly between the disassembly in IDA and in the debugger. Other type of stuff like that is objects. Very important to know, like name of objects, the names of structures, the different fields. You don't want to see EAX plus 14. You want to see, let's say, some vtable plus read stream, or you want to see like object.method, or you want to see the actual type that's in there. So after that part's complete, the second part is to close the loop. So phase 1 is going in one direction. It's going from the disassembler to the debugger, just one way. Phase 2 is where the loop gets completed. We take information from the debugger and feed it back into this assembly. And we start creating this loop that is going to provide a lot of the commenting and a lot of the data analysis for us without doing very much work. And phase 3 is we have all these disparate tools. We have disassemblers, we have debuggers, we have plugins, which are really just trying to patch tools we have to work together. None of the tools really work together. So what I envision is we have a standard API or interface, somewhat like a software JTAG. So there's one interface, and I could use IDA for disassembly, I could use WinDebug for debugging, or I could use Ollie, or I could use GDB. It doesn't matter. It's all going through one interface. So to do that, all we have to do is write plugins for all the different debuggers, all the different disassemblers, different viewers. And this provides us the ability to run whatever tool is most appropriate for the situation. Let's say you really like WinDebug because of the type information it provides, or you really like Ollie Debug and you like some plugin with it. You can use any type of viewer if you want. Let's say that you don't like IDA because of its licensing, or they won't give you a license because you're an independent researcher and they only want to sell to companies. So you can create another viewer and still use the whole subsystem, use the same debuggers, everything will work together. So that's what I've been concentrating on, is working on that. I'm going to try to have something working on that around CanSec next year, at least some kind of proof of concept, working at least with IDA, WinDebug, and Ollie Debug, perhaps GDB. So here's some of the differences between C and C++ from a reverse engineering standpoint. There's lots of indirect calls. So there's no cross-references. Cross-references is, let's say in IDA, bring it up actually real quick. So if you're not familiar with it, you can take a look. So let's see this read stream function right here. If we want to see the cross-references to it right now, all we see is the vtable. That's it. We don't know who's calling it or what's going on. All we know is coming from vtable. This is not very helpful. If it was C, we'd see all kinds of functions that call directly to it. So there's also virtual functions. Virtual functions are functions that are not defined in base classes, and anything that inherits from it is going to actually create it. So you're not sure, depending on where it's inherited from, what it's actually calling. It depends on the actual object type. There's also lots of glue logic and glue functions to do like RTTI and other C++ specific things, to look at vtables and that kind of stuff. There's also something called the this pointer. If you've programmed in C++, this pointer means it's the actual object. So if you want to call a method from the object and you're inside the object, it would be like this dot method. And in disassembly, this is going to be passed through a register for Visual Studio, Visual C++. It's always going to be passed through ECX. So now you have to look for arguments passed through registers as well as passed through the stack. So it's another thing that you have to keep track of. So here's a simple class. This is an example. It doesn't do anything, but it's just to show some of the different modes. So on top it says public. That means that the foo constructor and the foo destructor and the add method, those can be called from anywhere. The private section, the double X function or method, can only be called from within the class. So it can only be called from actually from add. You're not supposed to really call anything from the constructor and destructor. But you can only call it from the class itself. And the int x and int y, those are just private variables. So C++, what it really does with classes is it's creating an interface. It's saying you can use the stuff in public, everything else is hidden from you. It's just a box. So we're going to take this idea of the interface and use that for our reversing. Because if there's only certain things exposed, we can treat it as a black box and look how the outside interacts with it, and then at that class separately. And in C, it's anything can call anything. So in some ways, C++ is easier because you're being exposed to less things. It's more tedious and more complicated in the way it happens, but you have less data to worry about, and it's just a simpler interface. So like I was saying, it provides a defined interface. This interface is going to limit scope. So you can only call the private functions within the class. You don't have to those being called outside, because that is how C++ is defined. So if you understand this interface, you can understand from a higher point of view. I'm not talking about like understanding like C++ or assembly. I mean understanding from a developer's point of view. Why did they design the object in the class in a certain way. So it's kind of like, you could use a lot of this information as even like a design overview. What were they thinking when they wrote this software? Was there different objects? Why are certain ones inherited from other ones? And what are they trying to expose? Sometimes this doesn't work that well for badly written software, but that's the case for any language. But with well-written or decently designed software, you can get a lot of ideas how it works and how it interacts. And this is more like concept kind of stuff that it's not really even code. So a little more of an overview. What is a vtable? So a vtable is an array of pointers. And these pointers are all the methods within the class. So as we saw previously, here, this doesn't use a vtable, but for example, you see that these has a method foo, the structure foo, and the method $x. So if it had a vtable, we would see pointers to all those. And a vtable is used to make indirect calls. So if we look down here, the first assembly takes the vtable and puts it into EAX. So that's going to be the base of this array. Then it's going to add 14 to the base, and that's a pointer to some method. So that's going to be the sixth method within the vtable for this object. So this is how the vtable gets used. In the next slide, I'm going to show an example of a vtable so we can kind of see what it looks like, but it's just an array of pointers. So here I cut out a little piece of a vtable, and what you see is these are all 4-byte pointers, and they're pointing to all these different functions. And what the function I showed before was the read stream, the second one from the end, and we looked at to see the cross references for that. But as we see, all this is just a bunch of pointers, and that's it. This is how you make calls indirectly. So cross references and the story they tell. Cross references are extremely valuable. That's how you know how different functions, different methods interact. And through cross references is where we actually get insight into the design of the software and the program. And the cross references is the thing that gives us the concept of how the software was designed and how all the objects interact, the classes interact, and how it all comes together. It's all about who calls who and why. Why is certain functions and methods coupled together only from here to here? It's because there's some type of use and there's some type of design behind this. And what we use cross-references for is to determine what's public, what's private, and what's protected. Looking at something like this, we know that $x can only be called from within the class of foo, right? So if we have a vtable and we know all the methods within it, and we see that one of the pointers to the function only gets called from other methods, and it never gets called from outside, we know that's a private function or a private method. If we see it being called from outside of the class or object, we know that it's public. And if we see it being called from a vtable that is inherited, we know it's going to be protected. So this is how to determine this. So now, what do we have? We know all the methods of a class. We're going to know if it's public, if it's private, if it's protected. Later on, we'll look at how we determine inheritance. And this is all coming together. We almost have class diagrams based on this information. And it's all within the binary. We're not using symbols or anything to extract this out. It's all there. So we can take it a step further and use these class diagrams and generate some kind of UML-style graph. I'm not particularly fond of UML, but it has class diagrams. And if someone knows of a good UML library for Python to generate images, let me know after the talk, because I'm really interested in doing that. If not, I could just generate my own graphs. But basically, with all this information, you're gonna have the different, if it's public, private, protected, you're going to be able to tell which variables are private to the class and which ones are accessors, et cetera, et cetera. It's all there. It's all within the binary. And data coupling. Data coupling is interesting too. let's say you have different objects. Generally, based on the design of the program, you're going to have some objects that work with certain objects and not with other ones. And based on that, let's say that there's some objects that look at network traffic. So there's going to be probably network traffic, and maybe a parser object is going to work closely together. So if you see lots of calls between two different classes, two different object types, you're going to know that those are going to work together. So if you discovered the network stream object, and you see there's this other object that's parsing it, most likely that's not going to be accessed anywhere else. And it's going to give you more insight to how the program's working. You probably want to look at that parser to look for where the data is going, where it's traveling to. So some different implementations. Halvar released a library in Python. I think it's called relib. Most of the library, I think there's 5 files in there. Most of it's about graphing. Splitting up different functions, disassembly to display. There's a little bit of stuff in there for vtable identification. He uses a couple different methods to look for news to try to find constructors and find vtables that way. And there's lots of pretty useful helper functions in there. If you want to find all the cross references to a certain object, it'll create a list for you. If you want to find disassembly for a basic block, lots of useful helper functions. I've used it a bunch. There's also a new article on OpenRCE, which covers a lot of the same stuff that I'm going over here. He wrote some tools in IDC. He does vtable identification and does runtime type identification and some inheritance stuff. I haven't gone through all of it, but you can, the stuff I'm going to show here, you could use any of the methods here, or you could use the methods that I use to find this stuff, and you could use the same code and work the same way. It doesn't matter how you find the vtables or how you find this data. There's just different methods. Each of them is going to have cons. A lot of times when you're doing this kind of stuff, you're going to you're going to find vtables, you're going to miss some. There's going to be mistakes. You're going to have to go back over and verify, but a lot of this stuff is going to make it way easier. So I wanted to use IDaPython, and I wanted to use a debugger with it. The first thing I try to do is extend IDaPython to be able to use the built-in IDA SDK debugger functions. I ran into a problem that IDaPython uses Swig, and I don't know how many people have used Swig, but it's basically like a wrapper class. People use it for Ruby. People use it for Python, for different kind of stuff. And one of the big problems with Swig is it doesn't like variable length arguments like VA list. It doesn't support it. A lot of the debugging functions within the IDA SDK use that to pass arguments, so I couldn't do it that way. So the other solution was I could have some kind of custom marshalling of breakpoint handling, and that just started getting too ugly really fast. So I looked for another solution, and I used PyDebug. PyDebug comes with PyMay. Pedram wrote it. It works really well. Works right out of the box. Does a lot of things that you'd want to do for running a debugger, and it's all there. The code I'm going to show that looks at vtables is very short because of the libraries I'm using take care of a lot of stuff. So this is the algorithm that I've been using to look at indirect calls and cross-references using runtime. So first you find the vtables. There's different methods to find it. You could use one of the ones listed earlier. If you're reversing Microsoft stuff, which most people that are engineering are doing, because that's where the money is for vulnerabilities and exploits. And if it's in the standard OS, you're going to have symbols. And with symbols, you know where all the vtables are. The vtable, there's symbols called vtables. Like right here. This is debug help.dll, and it tells you it's a vtable. So there's no work to be done for finding them. So what you're going to do is you're going to set a breakpoint on all the methods in the vtable. When then you write some test code to execute the program, or maybe you just run whatever software it is, and you're going to start hitting those breakpoints as the program's running. Once it hits the breakpoints, it's going to look on the stack and see and figure out who called it, and then it's going to go to that location and create a cross-reference for the function or method that just got called. It calculates the sets a cross-reference, and if you want, you can also set a comment into the database so it shows you where it's going. And I'm going to show an example of this. I'll demo an example of this and show you how it works. But basically, this is ideally what we want to do. Excuse me. This is ideally what we want to do. We don't want to see this on the top. We don't want to see EAX plus 14. That tells me nothing. What we want to see is something like that at the bottom, where it says object. And we want to be able to, once we find a function or a method that we're interested in, we want to be able to look at the cross-references and have it tell us this big list of everywhere it's being called from. And let me do a demo real quick and show you how it works. So we looked at this before, this read stream function. And we look at the cross-references right now. All it shows is the vtable. So I'm going to be running this script here. As you can see, most of it is printing out debug stuff, and it's really short. It's like 80 lines long, and this is going to create all the cross-references for us. So all you have to do is highlight your vtable. And then you run the script. Those are all the functions being called. It's done now. Now we can take a look at that read stream function again. And look, this is all the cross-references that we've now determined. So then now we're doing this, right? And so there's one flaw in this right now that let me bring that back up again. But there's one flaw in that right now all we're looking at is execution path, right? It's only what is actually being run. But you can take this, and once you know some of the objects and some of the methods, you start reanalyzing, because a method can call one or two object types. If you trace the registers through, even code paths you don't take, you know what kind of object it is, and you can backtrace and fill that in. So what has to happen now is all these breakpoints you've hit, you store them in a list, and then you reanalyze all the functions that called it, and you start backfilling all this information. And after you do that, you can you start backfilling all these cross-references. Anything that's missing that you don't have there, you could create another and print that out, create a text file or whatnot, or another box within IDA, and then you can go back and try to fill those in. So this is what I'm talking about. You keep on doing this loop, you reanalyze, and then once you do that, you can also take all the locations you don't have data for and try to figure out what runtime path is going to get you there. So you could set breakpoints up until that point, then see how you modify your data to get to the next section, just to get to that code path, and then you start filling in more data. So keep on doing this process, and pretty soon you have all the info you need. So this is what I'm talking about. You take your known runtime data and you apply it to the rest of the function. And you keep the list of the cross-references, and you keep analyzing whatever functions and methods you've hit. Something else that is crucial that needs to happen is debugger type info. So I'm sure lots of you used Ollie debug. Let's say a register like this EAX, and it's pointing to a string. It's automatically going to dereference the pointer and see if it's a string. If it is a string, it prints it out. So why isn't it not doing it for other types of objects? It's only doing it for the string types. So if you have an object, I want it to say my object type. I don't want it to say some random number that I have to try to keep track of, write it down on a little piece of paper, and it changes every time I run it because memory gets allocated different. It's on the heap, so that changes time, right? It has all the information it needs, so I want to be able for it to tell me what type of object it is. I mean, it's silly. So how do we do this? There's a couple different ways. One way is, how about we set breakpoints at every constructor and every destructor, right? So we maintain a list of objects whenever we hit a constructor. We're like, okay, this memory address is going to return in EAX, because every constructor is going to return the address in EAX. We say, okay, this address is going to be this type of object. And then whenever we see one of those addresses in a register, we say, okay, it's that type of object. So one problem that we run into when we do this is constructor chaining. A lot of times you have an inherited class, and it's going to call the constructor all the way up to the base class. So it called like 5 constructors. What type is it? I guess we'd have to keep track of what the first one was. It starts getting a little bit complicated. Sometimes you call base constructor, sometimes you don't. It depends. That's one way, but it does have problems. Another way is back to our vtables. If you look at an object, the first keyword on it points to the vtable. So we know that has a vtable, so just like looking at a string where it just dereferences and sees if there's a string there, how about we just dereference the pointer and see if that points to a vtable? That has our object, and then we know our type. There's problems with this too. Sometimes when you have inheritance, you might have multiple vtables, but this works good enough. There's always going to be exceptions. There's always going to be problems. I haven't really figured out how I want to do that, if I want to look at multiple vtables or not, but this works right now. So how do we do this? In Ollie debug, I started to reverse Ollie debug to figure out where it does the dereferencing of a string, so I could just hook that function and also try to dereference objects. That's one way to do it. I haven't reversed all of Ollie yet, or at least the parts I need to find that. Within IDA Pro, you can patch the debugger similar to Ollie. All of IDA's executables, plugins, and stuff are all packed with ASPack, and so it's kind of a pain in the ass. You have to unpack it, and then you reverse it, and it's not the same. You're going to see in the it's kind of a pain in the ass. Another thing you could do is just, since IDA uses separate windows anyways for all their stuff, you could just create your own register display that only pops up when you hit a breakpoint or when you step, because you have all those events anyways. So don't use the regular register window. Use the new one, and it's going to display type information, and that's it. It's just an extra plugin. So inheritance. How do we determine inheritance? There's a couple different ways to do it. One of them that I've been using is constructor chaining. You can tell if something's calling another constructor up higher within a different vtable, because you can call multiple constructors within your own vtable. That doesn't mean it's inheriting. That just means that there's an overloaded constructor. Then you know that it's an inherited class. Another thing is scope of methods, how it's being called, if it's calling another vtable, basically kind of the same thing. Then we also have, if you ever see a vtable that has pure virtual in it, that's obviously a base class, because that cannot be called. Another thing you have too is you have different vtables, right? And if at the same offset it points to the same method, there's inheritance involved. Because if the EAX plus 8 is a certain location, and 2 different types of object can be that means that it's going to have the same method if they share that method at the same offset. So all you have to do is look at these vtables, see if any of them match at the same offset, and boom, there's some type of relationship between those 2 classes. So the same type of thing that can be done with the UML style graphs with displaying public and private, protected, whatnot, can also be done for inheritance. So pretty soon you can come up with this whole kind of program design UML graph for binary code with almost nothing. So this is also the thing that I think will make a lot of things work faster and work together, is this whole standard API, standard interface between tools. I think this should be an open interface. I'm going to pretty soon maybe start up a website, have blocks on there. It'll be all free code, because I want people to be able to use it and use it freely. So it's kind of like a software JTAG is kind of the concept. Like a hardware JTAG still has compatibility problems. It's not perfect. Like different tools don't necessarily speak the same JTAG, but it's just kind of like a concept that I want different tools to be able to work together through the same interface. And I haven't determined how I want that to work yet, but that's the basic concept. That I want different viewers, disassemblers, debuggers, whatever it is, to be able to be swapped out. And this is not just for runtime. Asm right here gave me like a great idea, was that taking the IDA disassembly, whatever data that you have from that, and how about if you feed it into MATLAB? That has beautiful graphing functions, beautiful analysis, and stuff like that hasn't really been done. So what has to happen for this to work is there's not a lot of work actually to it. The interface and the API has to have been developed or whatnot, but every tool is going to need a plugin to be able to talk to that interface. Registers, machine-specific information can be abstracted out. I would love to be able to use one controller and be able to have that talk to my cell phone, which is running ARM. And it doesn't matter that it's a different CPU as long as the debugger that's running on it speaks that same interface. Or it could be talking to like a PPC machine, or be talking to a Spark running Linux. It shouldn't matter what the OS and what the processor it's running. Some problems and some downsides of this is it's definitely not for anything that's going to have anti-debugging. If you have a standard interface, it's very easy to detect that you're being debugged because you have to communicate through the standard. So this is not going to be useful for doing like malware analysis or any type of anti-reversing type of stuff. So I'm going to show a little bit more of the code and stuff, but the whole idea is that we have all these separate tools. They're not talking together. They need to talk together. It can be way more efficient than it is right now, and it's not really going to take that much work. And we can come up with like a coupled framework. I think PyMay is really a step in the right direction, and getting that to talk to different tools is going to be one of the first steps. But this is how it has to go, because right now we're kind of limited to what we have, right? We have IDA. It comes from, that's like the disassembler. It comes from one vendor, one location. If you have tools for that, it only works with that. It has a debugger in it, but the debugger kind of sucks. I don't know how many of you guys used it. I've used it out of necessity for debugging ARM stuff, but it needs to work with other tools. And I think everyone will benefit from it. So I'm going to go over real quick how simple the code was to do the cross-reference stuff, and you'll see you'll be able to do this kind of stuff the same. Hold on for a second. Keeps getting unplugged. So all we do is we look at a selection, and we set breakpoints on the vtable. That's all this function here does. We create a handler, and all the handler does is figure out who called it by looking at the stack, looking at the ESP register in this line, and then subtracts 1 from it and finds the head of the instruction, and that's the caller. And then this line here creates the cross-reference. That's all this is. The rest of it is just like setup stuff. That's it. And comments. And this is 80 lines with all that stuff in there. I mean, there's not a lot of code. So, and then you have all the cross-references, and you can, the next version that I'm going to make of this is going to, it'll have a GUI. It'll have different methods for picking out vtables, so you can select, do you want to use the symbol vtables? Do you want to use the method from Halvar's RElib? Do you want to use the method that is in the OpenRCE article? And then it'll pop up all the vtables. Then you select which ones you want to use, and then it'll run it through. It'll tell you which ones were accessed, which were accessed, and you'll be able to work from there. So that's it for the presentation. Look on the blog for code, and now I'll take questions. The code, right now all I have is the simple script. That script, I'll put it on a USB key if you want to find me later. And I'll also put it on the blog when I get back. I'm going to be down here for probably about a week, so it'll be in about a week when I get back. But The full version that has the GUI and all that stuff, that's probably going to take another couple weeks for me to finish. I'm testing that, and I'm also testing the PDB generator and a ELF symbol injector. So those will probably 2 to 3 weeks. Those will be out. Is there any other questions? In the back? Uh-huh. So your question is, am I going to be able to, or you, whoever is going to be able to determine if it's two objects of the same class? Is that your question? Well, every instance of an object is going to point to the same vtable. Mm-hmm. Yeah, I'm not looking at, I haven't done that yet at all. As far as I've gotten on that is just to have debug type info on object type info in the debugger, so you could tell that it's a different, it's the same object type, but it's going to be at a different address. But I haven't looked at separating different instantiations from each other. Well, I'll take a look at that. It's a good idea. Any other questions? Yeah. Another thing that I was going to look at too is right now all that's being I'm doing right here is just methods, but also looking at private variables and how those are accessed, because I think that'll be helpful too. Any other questions? Yes, I'm reversing the PDB format. Code has not been released. It's still beta testing right now. Actually, this right here, the file that we were looking at, is debughelp.dll, and this comes with WinDebug. And this is the file that is used to load up load up PDBs. So I've been reversing this to figure out the format. Right now, I've just done global, and then next step is local. But the difference between them is the type within the PDB. PDBs are stream-based, so it's almost like a file system where you have different blocks, and it's not in order, and then you're going to have like a directory, and that tells you where the streams are all located. I can talk to you afterwards. All right. Any other questions? All right, cool. Viva la revolución, and I'll see you guys later. Yeah. Well, I was going to look at who is accessing it from what method. So if it's only being accessed from the methods in the vtable, or if it's being accessed outside. There's generally no public variables, and like no one does public variables really. In general. Yeah. Yeah, that's a problem. But if it's not in the vtable, then I usually have an actual address, so I have a cross-reference. Luis, nice to meet you. Do you do a lot of reversing?